geometric effects in semiconductors and superconductors.
Okay, good morning everyone. So first of all, I should thank the organizers for inviting me here, as I always like to come to São Paulo, which has a lot of things that Rio de Janeiro does not have. So today I'm gonna tell you things about what I call the quantum geometry, especially in semiconductors and superconductors. And in semiconductors, I will try to argue that this quantum geometry is actually very universal and it affects almost all the optical properties of semiconductors, even in the macroscopic scale that you can actually just look at it. And for superconductors, it's also very significant. Namely, actually the Meissner effect is just is of the origin of this quantum metric. So, so first I would define what I mean by quantum metric, and also related to the dielectric and optical properties of semiconductors. And from there, I will try to argue that you can actually use the optical effects to in turn determine the quantum geometric properties of semiconductors, including to detect this thing that has been highly discussed in the density functional theory called the spread of Wannier function. Yeah. And then I will introduce a little bit about the Meissner effect and superfluid wave marker. And actually, I'm just going to talk about this briefly to encourage you to talk to my students' poster. And then I will also discuss a little bit about the real space quantum metric of solids, which is another poster of my other student. And finally, I will try to draw some relevance, since there are a lot of field theorists here, about this very interesting property that, namely, if you apply this concept of quantum metric into topological materials, then you can actually get an Einstein equation for the momentum space of these topological materials. Now, first, let me acknowledge my collaborators. So the first part of the talk will be, it was the work done by my student, Luis Castillo. And also I will show some experimental data in collaboration with our experimentalist in-house at PUC, mainly done by this Chinese student Shai Zhang, and also in the group of Professor Lazaro. And also a lot of part in graphene is a collaboration with Dennis Kohan, who is now in National Cheng Kung University in Taiwan. And these are my two students that you will see here in the conference, that David Poyes and Lucas Oliveira. Okay, first, what do I mean by quantum metric? Yeah, so I'm interested. So actually, the condensed matter people have converged to call this thing quantum metric, but it really is just the Fubini-Study metric that you call in high energy physics. But I'm talking about Fubini-Study metric for a particular quantum state, namely the block state of an insulating material of a semiconductor or a superconductor that has a full band gap. So what do? You suppose you have a semiconductor or superconductor that has multiple bands, and because they're fermions, so you need to consider this fully anti-symmetric Slater determinant of the state. And from there, you can construct a correctly normalized state that depends on the momentum of the electron, right? And then what do? You simply consider, so this is how I like to think about it. So a block state is a unit vector in the Hilbert space, or in the Fock space if it's a many particle state. And it's a unit vector pointing at some directions, right? As you move from a momentum k to k plus delta k, this unit vector is going to rotate to some other directions. So, and then what you can do is you can take a dot product between those two states. And so essentially you are just taking a dot product between two unit vectors. So then, you know, the result is like a cosine of this angle between them, right? So if you expand it to leading order, then it will be quadratic in this small distance in momentum. And the coefficient in the front is what I call the quantum metric. But as you can see, it is really just a Fubini-Study metric. And we have also learned in this conference that this metric is appears everywhere, right? For instance, it appears in this complexity of quantum operations and so on. But today, I'm really just going to talk about it, particularly for the block state in the momentum space. And as you can imagine, it is going to be some Taylor expansion of this state that you are under consideration, which is this partial mu is the derivative over momentum in some direction, right? And also you can write it in terms of the original single particle states. So this is many particle state, but if you express it in terms of the original valence band state and the which I call N, and the conduction state that I call it M, then it really looks like this. It is summing over the derivative over momentum on the valence band state product with the conduction band state, and then sum over all these possible derivatives. Yes? They are orthogonal. Oh, well, no, at different cases, they are not orthogonal to each other. At a specific case, this N and M are all orthogonal to each other. But at different momentum, they are not in general not orthogonal to each other, right? And okay, so, and from there, many people have proposed that just by looking at this form, you know that it must be related to some optical properties of the semiconductors. Because, for instance, if you look at the optical conductivity, which is essentially the transition rate of electrons that has been excited from the valence band to the conduction band, if you apply a field, you apply an electric field, right? An electric field enters the perturbation Hamiltonian as interperturbation Hamiltonian, like a, yeah. So like H is like E dot X, right? So, or let's say in the position space is gonna be something like, but this is gonna be something like in the momentum space will be just I partial mu, right? So just from a Fermi golden rule argument, you can see that it is really just taking derivative on the field state and the transition rate to the empty state, and plus this part that conserves the energy, as you know of. But you have to multiply by a frequency. That's just from the Maxwell equation here. Yes? Yeah, well, I only want to look at the diagonal elements, because only the diagonal elements are related to this transition, because you need these two derivatives to be the same, right, in the Fermi golden rule. Okay, so many people have pointed this out. But today, I wanted to show you that not just the real part of optical conductivity, actually a lot of other properties are also given by this. So let's go back to a solid-state physics lecture course and review a little bit how we discuss the optical properties of semiconductors. It goes like this. It's very simple. You shine the light, some electromagnetic wave, into the semiconductors. Then you ask, what is the wave equation in semiconductors? Well, then you have the usual wave equation, right? But all the effect of dielectric is embedded in this complex dielectric function, which you can also write it as a square of the complex refractive index. Yeah, and this is almost like the definition of this quantity. And now there are two different ways that you can think of this dielectric function. You can think of the effect of the oscillating electric field of the light is to polarize your charge and to make the charge positive and negative charge in a dielectric to oscillate with time, right? So this way you think of it as like a charge susceptibility that is frequency dependent. Or you can also think of this oscillating positive and negative charge as an oscillating current, and that way amounts to a definition of optical conductivity. But there's just derivative of over frequency just from the, again, from the Maxwell equation, yeah. And then refractive index, once again, is also complex. And you, of course, you know that the real part of refractive index tells you how the speed of light is changing inside the media, and that gives you, this kind of bending of the light in the dielectric, right? And the imaginary part of refractive index tells you that how far the light can propagate into the media before it decays. Or you can also define it in terms of this absorption coefficient. The decay length of this is precisely determined by the imaginary part. So all this is that, and also in addition to that, another quantity that is easily to be perceived in the microscopic scale is the reflectance of this material, which you get by matching the electromagnetic wave at the interface between the air and the something that has a refractive index, right? So and so therefore it is expressed in terms of refractive index in this way. So the reason that I wanted to show you all this formula that you have already known since for ages is to emphasize that because of all these relations here, all of them can actually be expressed in terms of the real part and imaginary part of the optical conductivity. Because you see, they're all related to each other one way or the other, right? So at the end, you must be able to express any one of them in terms of these two. However, these two are also not independent from each other because there's a Kramers-Kronig relation between them, because one is real part, the other one is the imaginary part, right? And previously, I have just argued for you that the real part of optical conductivity at momentum k is given by this quantum metric multiplied by this delta function in the Fermi-Golden rule, right? Except what you see in real space of a real semiconductor is the integration of this optical conductivity in momentum space, no? Because you look at it in a macroscopic scale. So the punchline of this whole argument is the following. Now you do a Kramers-Kronig relation. Now what's gonna happen is that this delta function part is gonna become some other frequency-dependent kernel, right? But the quantum metric itself is independent of frequency, and therefore it remains there. Yeah. Therefore, you see that as a result, both the real and imaginary part of optical conductivity are given by the quantum metric multiplied by some energy-dependent kernel. And as a result, all these optical properties and dielectric properties are all containing the effect of quantum metric. Yeah. So as a result, I argue that the quantum metric actually determines all the dielectric and optical properties. In other words, it actually determines a very large part of how we see the world. Yeah. Yeah. You take a piece of insulating material, you put it under the red light, it appears darker than you put it under the blue light, and that's because the quantum metric has some effect there. Yeah. Okay. So given this, I would like to ask the following question. Can we use some optical properties to determine this, to sort of indirectly measure this quantum metric in momentum space? And in particular, just for the sake of my discussion, I will introduce this quantity, that is the quantum metric integrated over the momentum space. Remember that this quantity is defined for the block state at the specific momentum, right? But now I want you to integrate it over momentum space. And just for the sake of discussion, I call this the fidelity number. Now, this thing is interesting because we realize that it is related to what we call the Wannier functions. So Wannier functions are like this. Essentially, it is just the atomic orbitals of the atoms that make up the solid at the first place, right? So if you have this tight binding model picture, you ask how do you construct the electrons inside a solid? You say that, okay, you first solve each atoms, the Schrödinger equation, what are their orbitals, and then you put them closer and closer in together such that the wave function overlap, and then the electrons started to be able to move around. So there's a way that you can, from the block state, which is this is what I call L of K, which are either the valence band state, the N, or conduction band state M that I showed you in the previous slide, and just take a Fourier transform. Then you get the basically this Wannier function or the atomic orbital at any site that you want. Yeah, you just Fourier transform it back to real space. Now, then you can, so this Mazarian and Vanderbilt in 1997, they proposed this thing called the spread of Wannier function, which goes like this. You take the Wannier function that is centering at any site, for instance, at the origin, and you look at the variance of the position. So essentially, it's the distribution of the charge, yeah, of this Wannier function minus the position and then square. So this is really the variance of the position or the variance of the charge distribution, and they call it the spread of Wannier function. And this thing contains two parts. One's the gauge invariant part I call omega I, and the other one is the gauge dependent part. Now, the big question in the density functional theory is how do you choose a smart gauge such that you can minimize this gauge dependent part as much as possible, leading to a so-called maximally localized Wannier functions. And this is very helpful because then you can use them to construct some time binding models that are very short range, so it's very easy to solve. But this is not my concern today. My concern is how do you measure this gauge independent part? Yeah. Now we come out. It turns out that it has been proposed in 2000 by Sosa, Wilkinson, Martin, saying that this gauge dependent part it looks very much like the gauge, like the whole thing, but it's just some modification. It turns out that it is equal to the trace of this fidelity number that I have defined. Yeah. So then good. So but previously I have just told you that this quantum metric is related to optical properties. So can we use some optical properties to measure this fidelity number and then in turn determine this spread of Wannier function? Now let me show you that this is entirely possible. And it's actually very, very simple measurement that has, yes? That's a very good question. I think not directly, because you want to, yeah, okay. Actually, I think this might be some issue that remains to be clarified. Actually, it's more like quantum Kramer bound, because because there are also some research saying that this Fubini-Studi metric is the pure state limit of the quantum Fisher information matrix, and then there you can talk about Kramer bound and all that. But I think in solid state physics they haven't really talked about this yet. Yeah, that's a good question, but it seems like at least people have not thought about it in this way. But yeah, okay. Now let me show you that this is actually entirely possible to do, and it's actually very simple. So it goes like the following. I go back to this relation between the complex dielectric function and the complex optical conductivity that I've shown you in the earlier slide. Now I write it just in the tensor form. Then because I have already shown you that the real part of this guy is the quantum metric, right? So, but there's a factor of I here. So you actually want the imaginary part of this dielectric function. So imagine the following process. You take the imaginary part of dielectric function as a function of frequency, you integrate it over frequency and then multiply by some correct units. Then you got exactly what I call a fidelity number. Yeah, and this is actually a very simple measurement and has already been done since the 1960s. Yeah. So what they do is, for instance, the dielectric function of silicon, and actually it's bismuth telluride, which is the topological insulator. Surprisingly, it has already been measured since the 60s. You look at this green line, which is the imaginary part of dielectric function. So they measure it by this so-called ellipsometry measurements. Yeah, they send in a light that is polarized in some direction to hit it, and then measure. When the light is reflected, it will be rotated. The polarization will be rotated. And then from these angles, you can figure out the complex refractive index, and then you can use that formula to get the dielectric function. A very simple measurement. As you can see, these are all measured a long time ago. So the proposal is very simple. You simply measure the area of this curve, because I wanted to integrate over frequency, and then times this numerical constant that comes from a conversion of a bunch of fundamental constants, and then multiply by the area of the unit cell divided by angstrom, and that's it. You get the spread of Wannier function without any fitting parameter. So that's sort of the punchline here. You really just get from experimental data, you get a spread without doing anything. Yeah, without the need of doing any calculation. And from there, for instance, we use this experimental data to figure out what a spread of Wannier function. Again, that's just the size of atomic orbitals. Of silicon, which is around 70 angstrom square, germanium is about 83 angstrom square, and bismuth telluride is about 400 angstrom square. Yeah, and once again, completely without fitting parameter. Okay, now I'm done with 3D. Let's go to 2D. So 2D materials are a little bit different because you don't really talk about the wave equations in 2D. You don't really propagate inside 2D, right? Because you don't have any thickness. But one thing you can do is you can talk about these optical conductivities. They enter as the absorption power of the 2D material. So imagine you shine the light to a 2D material. Some part of it will be absorbed by these 2D materials, and once it passes through, it will become a little bit more opaque, right? So the opacity is precisely calculated in this way. You ask what is the absorption power? This is very easy because you create an optical current, right? So the current multiplied by the field, it gives you the absorption power. And you average over time and write it in terms of optical conductivity, so it's precisely this guy. So the absorbance, or equivalently the opacity, if it's in the visible light range, is precisely this absorption power divided by the incident power, which is nothing but the Poynting vector times the area, right? So, and then once again, you see that this is precisely given by optical conductivity, and therefore it's just the frequency multiplied by this spectral function of quantum metric that I introduced earlier. Therefore, the spread of Wannier function, you can easily be figured out by dividing this absorbance by frequency and then integrate over frequency. Now, actually, this formula you have already seen earlier in Dr. Juricic's talk yesterday, right? So he was also talking about optical conductivity. Now I'm just relating it to the absorbance, which is actually a physically measurable quantity, right? So for 2D material, you immediately think of graphene, right? How do I apply this thing to graphene, and what do I get? It turns out that graphene is actually a very interesting subject by itself, because we also have seen a few times in this conference that it has this Dirac cone in the low energy dispersion, right? But to get the right spread of Wannier function, you actually need to consider this tiny gap caused by the spin orbit coupling, which is of the order of 10 to the minus 5 electron volt. So usually you would say you don't care. You have a Dirac cone that is 1 electron volt wide. This teeny bit of a gap that is 10 to the minus 5 electron volt, usually you don't care, and usually it does not really affect any optical properties. But it turns out that to get this spread correct, you actually need this tiny little gap to have a finite result, and the result is 2.36 times the area of the unit cell on the hexagonal lattice. And okay, and also earlier in Professor Juricic's talk, he also gave some motivation of studying this twisted bilayer graphene, which is sort of a hot topic at present in condensed matter, because they found the superconductivity there, right? So at some small twisting angles, the bands are becoming particularly flat, and they also find that in this case they see superconductivity. And in particular, there's a class of theories. So there are many theories, so this is still under debate, right? So at least one class of theories saying that the superconductivity might be related to the quantum metric of these flat bands, yeah? So the detail I wouldn't be talking about, and to be honest, I don't quite understand either. But my interest is more like, okay, if you say that it's related to quantum metric, how about let's measure it, yeah, by some optical means. So I want to ask if we can optically detect the quantum metric of the flat band. Yeah. So to theoretically tackle this problem, we use this type binding model of Bennett et al., which is sort of a very simple 2x2 type binding model, but they claim that they are able to fit a wide range of twisting angles. Yeah. And our result of simulation is this. So I show you 5 columns, and each of them are in a different twisting angles here. And the first row, I show you the band structure of this, yeah. And the second row, I show you the profile of the quantum metric along some high symmetry lines in the momentum space. And also, I show you this fidelity number spectral function and the absorbance. So the key point is the following. Let's just look at these particular twisting angle, which is pointing 99 degrees, and in their theory, this is the flat band. This is the flattest out of this type binding model. The experimental data is like 1.07 degree or something, but it's close enough, right? So you see that the bands are really much flatter compared to the others. So we calculate profile of the quantum metric. In fact, indeed, it is very diverging. Yeah, but the question is, how do you measure this, right? So our proposal is again is very simple. You just measure the absorbance, but because of the bands are so much at low energy, the splitting is so low, so you will imagine that the absorbance will peak at some frequency that is precisely the band gap between these two flat bands. Yeah, so there are two flat bands, as you can see. There's two very, very flat bands. And because they are pretty much flat everywhere, and they pretty much have the same band gap, tiny band gap between them, as you can see, is less than 1 milli electron volt. Yeah, so the absorbance is gonna peak at this, because they're all the same everywhere in the Brillouin zone. It's gonna peak at this energy difference in between the bands, right? Which is less than 1 milli electron volt. So this is not gonna be an easy to do experiment because you need to use a so-called millimeter wave that is in this region. But nevertheless, if you can do that, you figure out the absorbance, you divide it by frequency, then you get this spectral function, and then you integrate over this area, you get precisely the quantum metric in the flat band. Yeah. And this way, and then you can do the same experiment for different twisting angles and see if it's really enhanced there. Yes. Yeah, so this is more like a non-interacting picture, right? So I'm really thinking, okay, if you just have these band structures without taking into account any interaction, you should have a strong absorption in this flat band thing. Yeah, but you are absolutely right. I didn't consider any other complications. Yeah. Okay, so this is sort of experimental proposal, and we realized that we can do better than this. So we further propose what we call a absorbance marker. So this is by drawing analogy with this concept, so-called topological markers, which is the concept which is sort of mathematical or numerical tool that can calculate a topological order in real space for some type binding model of the material that you're interested in. So without giving much details, the absorbance marker is very simple. It just contains some projectors to your lattice eigenstates. And this Fermi function ensures that you have projected from sort of a valence band state to the conduction band state, just like in the Fermi golden rule. And this derivative in momentum that I showed you earlier will become like a position operator in real space. So that's the sort of hand-waving argument. And you still have this conservation of energy that comes from the Fermi golden rule. And that's it. And then we try this to a disordered transition metal dichalcogenide materials, especially this material WS2, using this type binding model that right here in this corner. So we want to ask the following question: if you put some disorder into the 2D materials, which you can easily do for graphene, for whatever 2D materials, such as this one that we study. So here I show you what happens in real space. So this material, it has triangular lattice, and here I'm plotting the density of charges on every side, right? And we put impurities particularly on this side. As you can see, the number of electrons is suppressed because I put in some positive chemical potential there, right? And then we can calculate the corresponding absorbance in the same color code. For instance, this purple is really this on this side, and this red is really on the nearest neighbor side to this impurity, and this blue is the next nearest neighbor side to the impurity side. And the colored circles are really the spread of Wannier function in the absolute scale, yeah, for this material. And what we see is the following. Look, if you put in an impurity, you're going to suppress the electrons on that side. And as a result, there are less electrons occupying the Wannier orbitals. So your spread of Wannier function is reduced. So this is very intuitive. Yeah. But the catch is that you can really detect this by means of optical detections. And this agrees very nice with our experiments done at PUC. So at PUC, what we did is the following. We take this WS2, and then the blue line is the absorbance of this material as a function of frequency for the pristine WS2, yeah? And then we do the following. We put it inside a plasma chamber and hit it with some plasma. And this way you sort of produce some defects. And in particular, we think that the defects are you are removing these sulfur atoms, which are usually less bonded to the lattice. And if you remove the sulfur atoms, you're gonna remove some electrons there, and just like what we are happening here. And then the absorbance is gonna be reduced because some on the impurity side it is reduced. So on average, it will also be reduced slightly. And if you hit it with more and more plasma, then you produce more and more impurities. And you see that the absorbance you're further suppressed. Yeah. So this agrees very nicely with our experimental result, except this higher energy part. So these solid lines are the experimental result, and dashed lines are our theoretical calculation. And then you see that they agree pretty well up to here, and then they start to deviate. And we also understand why. This is because this simple 3-band type binding model only takes into account the d orbitals of the tungsten atoms, but the sulfur atoms they don't take care of. So, and the sulfur bands are in higher energy, so they also absorb light, and this is the effect of absorption of light due to the sulfur atoms. But other than that, we fit at least pretty well at this low energy part. Okay, and then comes the advertisement for my two students. So first of all, we discovered that a simple superconductor, S-Wave superconductor, you can find in any textbook, like Tinkan's textbook, for instance, that you treat it with the mean field theory. So the Hamiltonian looks like this, right? And where this delta K is the superconducting gap. And you diagonalize it, you have a empty quasi-particle band, and you have a field quasi-Hall band. And the field quasi-Hall band, you can also treat it like a valence band of a semiconductor, and then just construct the quantum metric of it. And the expression is very simple. In S-Wave superconductor is just given by the gap square times the group velocity in the normal state, and then divided by the energy dispersion to the fourth power. Now, what's the big deal of this? What's the big deal of this quantum metric? We realize that it actually enters the Meissner effect. And for more details, please see his poster. But just to give you some short description, using this topological marker formalism seem very similar to this absorbance marker, we can introduce something that we call the superfluid wave marker. Then this superfluid wave marker, it describes the Meissner effect under the influence of disorder. Yeah? And what we found is also very interesting. So here I'm showing you the diamagnetic current. You know the Meissner effect occurs because the superconductor generates a diamagnetic current that counters the magnetic field that you apply, right? So here I'm assuming that the vector field is pointing to the left, such that you generate a diamagnetic current that's all pointing to the right. However, if you put in many impurities, then the current seems to start to become turbulent. It's no longer uniform anymore, but it looks a little bit like, imagine you have a river, and then you put in some pebble stones into the river, then the flow is gonna become kind of turbulent, right? So it does look something like that. And moreover, the overall magnitude of the current is being suppressed compared to the clean case. And let me remind you that this is completely in agreement with the seminal experimental data by PIPA in 1953. So what PIPA did was he made a material more and more dirty. I think it's tin, if I remember correctly. Made it more and more dirty such that the mean free path is reduced. And he found that the penetration depth has been increased if you make the system more dirty. This you can find, again, in any textbook of superconductivity. Let me remind you that the diamagnetic current is essentially the inverse of this penetration length square. So that means as the mean free path, as you put in more disorder, mean free path is reduced, the superfluid wave is going to be suppressed, which is completely in agreement with the result that we get from this super free wave marker. And moreover, we tell you how the flow looks like in the microscopic scale. Okay, and for any details, please see my student's poster. Then, recently we also, this is sort of a digress. So we also propose a kind of real space quantum metric, which is applicable for any solids. It goes like the following. You have a solid, you have some ground state, Fermi C, or if it's insulating material, it doesn't matter. Some ground state. You apply the electron annihilation operator at a specific site of some degrees of freedom, like spin or orbit or whatever. You apply this to a ground state. This way, you can create a localized state. If you look at the wave function of this state, it really is localizing at the position of this annihilation operator. But just to normalize it correctly, you have to divide it by the square root of the density of the particle there. Yeah, and once you have this normalized state, you can also construct the Fubini-Study metric for this normalized state. Yeah, the quantum metric of it. And the simple physical picture is that you have a state that is localized somewhere, and then if you move it a little bit, yeah, and then you ask what are these overlap of these two states. If the state is very localized at beginning, then the quantum metric will be very large because you move just a little bit and then the wave function has been diminished a lot. Yeah. So, right. And what's the big deal of this? Well, because we think that this kind of momentum space quantum metric, you cannot do too much about it because they are all material properties. But the real space quantum metric is different because you can presumably engineer it by means of disorder. Yeah. And this will be very much similar to, how a heavy star deforms the space-time metric in an otherwise uniform universe, right? So you put a star, you put a black hole, you're gonna deform the Einstein metric, and then there's some interesting effect coming up. And we are thinking that if you put some disorder into a solid, then you can deform this metric, and then you can also talk about, for instance, the Riemann tensor, Ricci scalar, and all this stuff. Yeah. So, okay. And I encourage you to talk to this guy with a smiley face. That he will be happy to explain to you some interesting effects in this real space quantum metric. Okay. Now coming back to the momentum space quantum metric, as I have described since the beginning of the talk. I want to ask the following question. Now you have a metric defined a manifold, which is the momentum space. Then naturally you will ask all these differential geometric properties that you ask in the textbook of general relativity, right? For instance, taking a derivative of this metric, you get this affine connection or the Christoffel symbol, right? And then why are these interesting? Because they give you the geodesic equation of these in the momentum space. What is the shortest distance between 2 points in momentum space of some materials? And interestingly, this geodesic, within the context of this quantum metric, has the following interesting interpretation. Imagine you want to go to one momentum Ka to another momentum Kb in the momentum space. And at each point, I'm defining a block state, right? So the physical picture is more like at each point, you can define a Hilbert space, each point of your trajectory. And the quantum state that you construct, the block state, as I say, is like a unit vector in this Hilbert space. So you are asking, as you go from Ka to Kb, what is the trajectory along which this rotation of the state in the Hilbert space is the least? Yeah. So this will give you a nice interpretation. So you're going from here to here, and then you're asking what is the trajectory along which this state rotates the least in the Hilbert space. And then you can go ahead and take another derivative to calculate the Riemann tensor, and then take a contraction, you get a Ricci tensor and Ricci scalar and so on, right? And you can even ask what is the Einstein tensor if the Einstein equation is showing up in this quantum metric. And also you can ask if your momentum space is a so-called maximally symmetric space, meaning that your metric has the most symmetry possible. If that's true, then the metric and the Riemann tensor will have to satisfy this equation. Yeah. And then, okay, so I want to test this, particularly for topological materials, by which I mean you have also seen several times in this talk, that is in this conference, that the topological materials are all described by, or at least the low energy part are all described by these Dirac models, where you have some momentum dependent function multiplied by the gamma matrices. Yeah. And this momentum dependent function, they are even or odd depending on the symmetry class of the materials. Yeah. And the simplest model you can build up is this linear Dirac model, where you have one component of the this D vectors to be just the mass term of your, basically the band gap of your material. And the other two are just Kx and Ky of your two momentum. If I'm considering 2D, let's consider 2D first. But because I want to solve it in polar coordinates, so I write it as k times cosine phi and k times sine phi, and multiply by the Fermi velocity such that the unit is correct. And then you go ahead and calculate the quantum metric in the polar coordinates. They look like this. Yeah, they only have diagonal elements in the polar coordinates, and it's depending on the dispersion in this way, and also here n is the dimension of your Dirac Hamiltonian. And you can also calculate the Riemann tensor. This is non-zero elements, and you can also calculate Ricci tensor. It turns out it's like this. And the geodesic equation, you just put the affine connections into this and solve it, right? And by the way, this form of the geodesic equation looks very much like the Kepler problem of the Earth orbiting around the sun. Yeah, at least you can solve it in the same way. Okay, but these are all maths, right? Are there some interesting differential geometric properties coming out of all these formulas? I found that there are several interesting things. First of all, the volume of the Brillouin zone is a constant. How do you calculate it? You just take the volume form, which is the square root of the determinant of the matrix, integrate it over your space, and it turns out it's a constant. That is only determined by the dimension of the Dirac Hamiltonian. It's a constant in the sense that it is independent of the band gap of the mass term m of the Dirac Hamiltonian. And the Ricci scalar is also a constant. That's also very interesting. And this has also been reported by Mazura and Rio in 2010. And it is also only determined by the dimension of a Dirac Hamiltonian. And just to draw some relevance to the theme of the conference, namely the topology, right? So you can talk about, if you have a 2D manifold, you can talk about the Euler characteristics. That is simply this, again, the integration of the entire manifold of the volume form times the Ricci scalar. And I have told you that Ricci scalar is a constant. So if you get this, you got really the Euler characteristic is 1, meaning that somehow your Brillouin zone is more, in the sense of topology, is more analogous to a perfect sphere that does not have any genus. And also, if you solve for the geodesic equation, it's quite interesting. The geodesic is always a straight line, despite the band gap could be larger, band gap could be small. It's always a straight line. And finally, the Brillouin zone is indeed a maximally symmetric space because this equation is satisfied. Okay, so that's 2D. And you might say that this is an oversimplified model, but you could actually regularize this thing on a lattice, where instead of using mass term and Kx and Ky, you just put it on a torus, right? So Kx will become sine Kx, and Ky will become sine Ky, and the mass term will have to regularize it in some additional terms. And then you can calculate all these things numerically. Then you still find that the Ricci scalar is a constant and Brillouin zone is still a maximally symmetric space. Yeah, and these are sort of the pattern of these a metric in momentum space in 2D. No. Actually, that's a good question. I think I remember it's still 1, but yeah, probably yes, because that's very counterintuitive. Because you have a torus, right? But nevertheless, the Euler characteristics defined from the Fubini-Studi matrix still gives you the Euler characteristic 1. Yeah. Then, okay, then coming to 3D, that is even more interesting. So the linear Dirac models in 3D is very simple. You just have 4 components. One is the mass term, the other one is kx, ky, and kz. But I want to solve it in the spherical coordinates, so I use sine theta, sine phi, and so on. And then first you can calculate a quantum metric, and it also only has diagonal elements in the 3 coordinates. And then you can see the Riemann tensor, and it takes this form. And the geodesic equations, again, it has this complicated form. But nevertheless, you can solve it. And what are the interesting things coming out of this? Okay, so I found that first of all, the volume of Brillouin zone is once again a constant, and it's only determined by the dimension of a Dirac Hamiltonian. And secondly, the Ricci scalar is once again a constant. Yeah. And surprisingly, the Einstein equation is also satisfied, and in particular, the vacuum Einstein equation. And moreover, it is satisfied with a finite cosmological constant. Now let me remind you that my manifold is a Euclidean manifold. It's not a Lorentzian manifold. Yeah, so I don't have a time dilation, length contraction, these kind of things. So it's a static manifold. It's just a momentum space of your Bloch electrons. But nevertheless, the Einstein equation is still satisfied. And then I have asked many questions. What does it mean that you in a Euclidean manifold that you have a finite cosmological constant? To be honest, I don't really know. But it seems like it just renormalizes your Ricci scalar in a way. Yeah. But it's not like you know, the cosmological constant usually tells you if the universe is expanding or contracting, right? But here there's no dynamics. Everything is static. But nevertheless, it's satisfied. And Brillouin zone is a maximally symmetric space again, and you still have a straight line geodesic. And once again, even if you regularize this on a lattice, yeah, you put kx into sine kx, ky into sine ky, kz into sine kz, and so on. All these are still the same. You still have a constant volume, constant Ricci scalar, and still have an Einstein equation, and so on. And I got this through just solving it numerically. Okay, and that comes to the end of my talk. So to summarize, first, I try to convince you that the quantum metric actually determines many dielectric and optical properties of semiconductors, including the real and imaginary part of dielectric function, real and imaginary part of charge susceptibility, and real and imaginary part of the refractive index and absorption coefficient, and reflectance and transmittance and all that. Yeah, so it really, you know, the optical property of any insulating materials is really given by quantum metric. And then I intend to argue that you can actually measure this spread of Wannier function in 3D from this imaginary part of dielectric function, and in 2D from this absorbance. Yeah, and also I introduced this absorbance marker to describe the impurity effects in the microscopic scale. And finally, I discussed the quantum geometric properties instead of, in summary, I found this interesting properties, namely the volume Brillouin zone, Ricci scalar, and Euler characteristics are all constants. And you have this straight line geodesic and also maximally symmetric space. And in 3D, you have an Einstein equation with a cosmological constant. And that's it. Thank you very much.
Thank you, Wei, for the talk. Questions? Yes.
Oh.
So thank you for the nice talk. So how do you actually connect this formulation with topological materials in the usual sense?
So when you talk about all these things here, right? So it really does not have a direct connection with topology. For instance, I'm talking about Euler characteristic, and I show you that it's a constant. But you say that, how about topological trivial phase and topological non-trivial phase? Is there a difference? The answer is no, there's no difference. So it's not directly connected to the topology in the usual sense. I'm really talking about it entirely within the framework of differential geometry. Yeah. And then you ask, okay, is this thing related to the appearance of edge state or this and that? The answer is no. There's no, so in this way, it's more just sort of a mathematical property of these things. Yeah.
So there's no way to actually relate any of that to, say, an obstruction or define a smooth gate on the torus. Because, it's very confusing, especially for students. If, a torus is a torus, it's topological in this mathematical sense. But of course, you need to have an obstruction to be able to.
That's a good question. Actually, for instance, if you look at the 2D class A, for instance, you have a quantum Hall effect or quantum anomalous Hall effect, right? So usually you define a Chern number from the integration of Berry curvature. And now I'm using I'm calculating Euler characteristic from this quantum metric and Ricci scalar. So it's really two different objects to talk about topology. Yeah. So the usual topology from Chern number is really what gives you the quantized Hall conductance and all that. And this thing you say, okay, it's quantized, but so what? Is it related to some physical measurables? I'm not sure. Yeah, I'm not sure. But up to here is more like a mathematical aspect to me now.
Any further questions?
No. You said that in the 2D is you have a sphere, but in the 3D, what's the form of the manifold that you get?
But as far as I understand, the 3D, to talk about topology is not that easy, right? Because so in this continuous model, the manifold is really an infinite space. It's a polar coordinate and infinite space. And you can see this just from, for instance, in 2D, I'm really integrating the radius from 0 to infinity.
Yeah, but it has a finite volume, right?
It has a finite volume, yes.
So it's compact. So S3.
Oh, okay. Good to know. Yeah. Oh, okay. I see. I guess it's good. It's good to learn. As you can see, I'm still learning this.
No,
the bottom line is I'm really using this as an exercise in differential geometry.
Right.
Yes.
No, the other question is, since you have symmetric space, you could explore the algebraic formulation of it, because that's, instead of looking at sphere S2, is the group SU2 divided by U1.
Okay.
And in the three-dimensional case, it might be SU2 alone. So you have SU2 in the three-dimensional case and SU2 divided by 1 in the 2D.
Okay.
So in some way you are winding up this U1 from 3 to 2. I don't know.
Okay, good to know. Yeah, maybe you can tell me more later. Yes.
Okay. In 2 dimensions, there are systems which don't have Wannier states, right? Like P plus IP superconductors. So there you cannot define this metric, right?
So again, in superconductors?
Yeah, P plus IP is...
P plus IP, yes.
Superconductor, there are no Wannier wave functions. So you cannot define this metric, right?
What? Okay, I have a chiral, you say chiral P wave, right?
Yes, yes.
And what do you want to calculate?
No, you want to construct a metric based on the wave functions, right? You use Wannier wave functions.
Oh, okay.
So
you mean because it has... No, actually, I'm not sure. Because so first of all, we haven't calculated the unconventional superconductors yet. But for this conventional superconductors, we argue that you can actually get the Wannier function of the field quasi-Hall states. You can Fourier transform, you just treat it like a block state. You Fourier transform it, you still get some localized state. But for P plus IP, well, if it's fully gapped, then I think it will still be localized. So what, okay, this I'm not sure. But for D wave, for instance, for D wave, if you have a nodal point, then what we found is that you Fourier transform, you get something diverging. Then you can really, actually, am I right? Yeah, I think if you have a nodal point, it might be more ambiguous. Yes.
I want to understand your statement about the absorbance of graphene.
Yes.
So you said that it was there was an infrared divergence that unless you added a small mass, it diverted. So
that's true.
It depends logarithmically on that. Curve?
It depends.
Is it logarithmically?
That's true. Absolutely. Actually, this is very easy to see because graphene is known to have a frequency-independent absorbance. So if you divide it by frequency, you'll be 1 over omega, and then if you integrate over frequency, you got logarithmic divergence.
The optical conductivity is constant.
Optical conductivity, yes, absolutely. You get it. Yes.
Okay, so if there are no more questions, we thank Wei again.
Thank you.